Welcome, everyone. Today, we'll dive deeper into operators in C, focusing on Part 2. Let's explore bitwise operators and their fascinating applications in programming. In this section, we'll cover the meaning and use of bitwise operators, including AND, OR, XOR, complement, and the left and right shift operators. These operators work directly on binary digits or bits, offering high efficiency in various computations. Let's start with the bitwise AND operator. It returns 1 if both corresponding bits of the operands are 1, otherwise, it returns 0. For example, the bitwise AND of 12 and 25 evaluates to 8 because only the third bit from the right is 1 in both numbers. Next, we have the bitwise OR operator. It returns 1 if at least one of the corresponding bits of the operands is 1. For instance, the bitwise OR of 12 and 25 results in 29, where any position with a 1 in either operand gets a 1 in the result. Moving on to the XOR operator. This operator returns 1 if corresponding bits of the operands differ, and 0 if they are the same. For example, the XOR of 12 and 25 gives 21. Notice how this operator highlights differences between the bits. The bitwise complement operator inverts all bits, turning 0s into 1s and 1s into 0s. For example, the complement of 35 flips each bit, effectively producing its ones complement. This operation is particularly useful in bit manipulation tasks. Let's take an example to understand the bitwise complement operator in action. Here, we are computing the bitwise complement of the number 35. First, we represent 35 in its binary form, which is 00100011. The most significant bit, MSB, is on the left. The least significant bit, LSB, is on the right. Now, applying the bitwise complement operator, we flip each bit. This turns 00100011 into 11,011,100, which is the ones complement of the number. Let's interpret this result in decimal. The MSB in the complement result represents a negative value, so we calculate it as -128. The remaining bits are summed as 64 plus 16 plus 8 plus 4. When we add these values, the result is -36. Hence, the bitwise complement of 35 is -36. Finally, let's discuss the left and right shift operators. The left shift operator shifts bits to the left by a specified number of positions, effectively multiplying the number by 2 for each shift. Conversely, the right shift operator divides the number by 2 for each position shifted to the right. Let me explain it with an example. Consider the decimal number 40. In binary form, it is represented as 00101000. Now, when we apply the left shift operator with a value of 1, written as 40 less than 1, all the bits are shifted one position to the left. The binary becomes 01010000. Let's understand it with a simple example. Imagine the decimal number 14. In binary, it is represented as 00001110. When we apply the right shift operator with a value of 1, written as 14 greater than 1, all the bits are shifted one position to the right. The operation essentially divides the number by 2, discarding the least significant bit and filling the leftmost position with a 0. After this shift, the binary number becomes 00000111, which equals 7 in decimal form. Now, if we apply the right shift operator again, this 14 greater than 2, the bits are shifted one more position to the right. The result is 00000011, which is 3 in decimal. Again, this demonstrates division by 2, performed twice. Let's briefly explore special operators in programming, tools that offer unique functionalities. The address of operator, AND, retrieves the memory address of a variable. For example, AND gives the location of it in memory. The pointer declaration operator, asterisk, is used to declare a pointer, which stores the address of another variable, like int asterisk p equals and a. Lastly, the sysoff operator tells us the memory size of a variable or data type, useful for optimizing memory usage. Operator precedence determines the order in which operators are evaluated. For instance, multiplication, asterisk, and division have a higher precedence than addition, plus, and subtraction. Therefore, in an expression like 3 plus 5 asterisk 2, the multiplication happens first, resulting in plus 10 equals 13. Next, we have associativity, which resolves conflicts when two operators of the same precedence appear in an expression. Associativity can either be left to right or right to left. For example, subtraction is left to right associative, meaning in an expression like 10, 5, 2, it is evaluated as 10, 5, 2, giving us 3. On the other hand, the assignment operator, equals, is right to left associative, so x equals y equals 10 assigns 10 to y first, then to x. C categorizes operators into several precedence levels. At the top level, we have postfix operators like increment, plus plus, and function calls, which are evaluated first. At the bottom, logical operators like and or, vertical bar, are evaluated last. As we continue our discussion on operator precedence and associativity, let us delve deeper into the specific operators and their precedence levels in the C language. Starting with relational operators like equals, equality, and equals, inequality, these are evaluated only after arithmetic and bitwise operations. For example, in the expression 5 plus 2 equals 7, the addition happens first, and then the comparison is made. Next, bitwise operators, which include and, caret, XOR, and vertical bar, or, ternary conditional operator, found at level 13. It is right to left associative and allows compact conditional statements. At level 14, assignment operators like equals, and compound assignment operators such as plus equals and asterisk equals. These are right to left associative. Finally, at level 15, we have the comma operator, which evaluates expressions from left to right.
Thank you for your attention. Bitwise operators are incredibly powerful for low-level programming tasks. Feel free to ask any questions or share your thoughts on their applications.